Hello, this video will help you understand how to get through problem number 20. I'm not going to do all the individual data points, I'm just going to do a collection of probably 5 of them, and it will give you the tools to go through all the others. So it's basically the pattern that's tricky. Once you know the pattern, it just becomes a long problem. But after this video, you should have a clear understanding of the pattern and at least feel confident that you know what you're doing for the solution. So right now I'm making a data table that will have the information that was given to us from the book and that very odd horizontal data table, which I really hate. So we have 0, 0 given to us at the beginning. We had 0.25 and 0.11. We had 0.50 and 0.46. We have 0.75 and 1.06. We have 1.00 and 1.94. So those are 5 data points that we were given. Hopefully you've already watched the video about the kinematic graphs. If you did, you'll know that if you go from a position versus time graph, then you find the slope, you'll get a velocity versus time graph. And that's basically what you're doing here, is you're getting a position versus time data table. You're finding a velocity versus time data table by taking that change, that slope. Okay, you're not seeing the slope, but it is what you're calculating. So over here, I'm going to have the time still on the x, and your velocity is your new y. To be able to figure out how to go from the position versus time and velocity versus time, you need to remember that the velocity equals the change in x over the change in time. It's a very important equation. It's not explicitly on your equation form or your equation sheet, but it is very important to know. Okay, the kinematic equations do use it, but they use it in a different form. So to make sure you're very clear, this section here is to be able to fill out for this variable. Okay, now to find the time, you need to find the midpoint, okay, which is basically finding the average, but I'm going to write t mid is t final, which is you can either use a t or a t1, plus t initial, all divided by 2. So you add the time that you ended with and the time you started with divided by 2. That will go here. Okay? So let's do a few, just to make sure you guys are very clear on that. First thing, I'm going to change the thickness here. So we need to do it with 0, 0 at the beginning, because if we had no position at the initial time, it's not going to move right away. So you can say that your initial time, you had a velocity of 0. Then we can look at the pairing. So these two here need to be paired. Okay? Maybe if I circle it, it will be better for you. So we have a green circle here for a pair, and this green circle here needs to be paired in order to use the velocity equation and get a value here. Okay, so you do 0.11 minus 0 divided by 0.25 minus 0, you're going to get an answer of 0.44. Now that's not what you use to find the time. So when you use the time, you're using, I should make the colors more different. Let's try this. If we use the time here, you're going to use these times, but it has nothing to do with the position because we're using the t mid equation, and that's going to go here. Now again, you should remember you're using the t mid equation because that's the light blue column, and so you got to use the light blue equation, okay, based on the highlights. So you're going to do 0.25 plus 0 divided by 2, which is going to be 0.12 5. Okay, now for the next one, you have to look at the next pair. So here's the next pair. So using those two, you'll get a value for this location. Taking the final, so 0.46 minus 0.11 divided by 0.50 minus 0.25, you'll get a value of 1.40. For the time, we will use just the times. You do 0.5 plus 0.25 and divide by 2, you're going to get, oh, I forgot to highlight, so dark green. You're going to get 0.375. Hopefully you're seeing a pattern. Next one is you get the pair here, the pair here, and that's going to go right here. I'll go ahead and show this one out, because if you're not getting it now, it means you probably need to see it. So I'm going to use the velocity equation for this one. So we got v here. I've been saying it to you, but this way you can actually see it in case you're having trouble. You have 0.106 minus 0.46 divided by 0.75 minus 0.50. Okay, and that will give you a value of 2.40. We use this here for the time, and just in case that's not being clear either, so I'm going to do the time here. You'll have the T mid for this location is 0.75 plus 0.5 all divided by 2. And that will give you 0.625. And you just keep on going. Okay, so the pattern keeps repeating. So that's how you go to the velocity versus time graph. Now you need to go to the acceleration versus time graph, which is very similar. It's really not that different. So you have time in seconds, you have acceleration in meters per second squared. Now with this, you're going to need to basically do the same thing for time. You're taking the midpoint, okay? The difference when you do the time over here, it needs to be from these values, okay? They completely ignore the time that's in the data table from the book. Okay, so you're using the new values, and actually maybe I should draw the arrow differently, because you're technically taking these values into the midpoint equation and then putting them in here. Okay, let's go ahead and do it like this actually. So these values go into the T mid equation, which is the same equation, T final plus T initial divided by 2. The only difference is you go from here, put them in the equation, and then those go in here. Now acceleration is very similar to the velocity, it's just the slope of the velocity graph. So the equation is going to be delta V over delta T. And that will give you what you need to know to take values from here, There you go. Okay. And you plug them in just the same way you did before with velocity. You're just using pairs. Now the difference, okay, is you do not plug in the 0, 0 on the top because your acceleration is not 0 at a time of 0. So we're going to use a pair. First pair we'll use is this one, and you have to use the pair for both of them. And when you take the 0.44 minus 0 divided by 0.125 minus 0, you're going to get 3.52. When you find the midpoint, you're doing the same thing, the same pattern as last time, so you're just going to get 0.063. The next pattern, sorry, not pattern, next pair, let's use gray. I haven't used gray yet. So next pattern is here, and this pair. So you take 1.4 minus 0.4, sorry, minus 0.44, so 1.4 minus 0.44 divided by 0.375 minus 0.125. You get a value of 3.84, and the time is 0.375 plus 0.125 divided by 2, and you get 0.25. I'm going to go ahead and erase this that I just put in there so I have room. Do one more. Just do, don't think I've done this blue yet. So here's a pair. Here's a pair. 2.4 minus 1.4 divided by 0.625 minus 0.375, and you should get a value of 4, so 4.00. And the time, you're going to take 0.625 plus 0.375 and divide by 2, and you get 0.50. Okay, so again, you're going to keep that pattern going. Okay, once you're done with the entire data table, all the points they have, then you graph velocity versus time and acceleration versus time. So I'm going to zoom out. Using the velocity versus time, so everything that you get from this pool of data, we'll make a graph. It's going to look a little wiggly, but whoops, not that wiggly. Okay, it's going to be sort of like, sort of like that. It kind of moves a little bit up. Maybe not quite that far, but it's pretty close. And what you're really doing there, because this moves kind of slowly, okay, it doesn't go up right away. You're looking for the average of the slope. Okay, so this is your velocity versus time graph, and the average of the slope here should be roughly 10.5. Sorry, so roughly 10.5 meters per second. Okay, be a little bit above, a little bit below, it's okay. And then your acceleration, so you're going to get these values, and you're going to go over here. Again, you don't have to draw these arrows I'm drawing, that's just for you guys to follow where I'm drawing it. So you have acceleration versus time, so this is going to be time. Then you have your acceleration in meters per second squared. it sort of starts here and goes up, and then it comes flat, and then it goes back down. Okay, you should have an average of roughly 5.3 meters per second squared. Now keep in mind the values that you write down should actually be to three significant figures. Um, so, for example, I had 5.32, but I'm not going to write that doesn't need to be that accurate for your answers. Your answer should be to three significant figures, but um, if you had like 5.2 or 5.4 or 5.5, it's okay to be in that ballpark. Even as low as 5 would be okay. You just want to make sure you're getting a ballpark figure. Okay, anything past 5.5 actually might be a little large because you'll be going towards the top end of that curve, and you needed to get an average, so there should be about as many above and below. So that's why you're looking at something closer to 5 than you would be at 5.5. But that concludes this problem. It's not uh, a complex problem as far as the equations. It's just more of a tedious problem when it comes to graphing and realizing the values and how to change them. But that should uh, at least make the pattern a little easier to see and allow you to finish the problem if you weren't able to do it when you first did your homework.